All right, welcome back to part two of our first step into this journey that is voice over IP. All right, so this is where we left off, and I feel compelled at this point to say, or at least remind you, that this is perhaps a vast oversimplification of all of these components that go into how these networks operate. So we're just sort of hitting some of the high points so that we can sort of understand how we got from where we were 20 years ago to where we are now. And these are just some of the basic ideas. Now, since I did all the beep boop boop sounds and I've talked about frequencies and things like this, let me remind you about a video that I did a while ago about frequencies. The public switch telephone network connection to a phone, the local loop, the tip and ring, that entire circuit is based on handling a couple of frequencies, or a range of frequencies, from 0 to 4,000 hertz. Why? Well, because that's the range of human voice. Now, you could make it handle a larger collection of frequencies, but that would require additional capacity from the network. And so everything that flows over that local loop connection, that tip and ring pair, falls inside that range of frequencies. That includes the numbers that you dial on your dial pad. That includes the signals that come from your local office. It includes the carrier wave that a modem would use. So all of these things have to fit inside this range of 0 to 4,000 hertz. Now, the little dial pad on a phone like the one in the bottom left is a collection of frequencies that also fits inside that band. So if you look right up there, right, we have the collection of frequencies that's on our dual tone multi-frequency dial pad. So every time you push a button, you're actually sending two frequencies. So in the case of a number 1, you would send 697 hertz and 1209 hertz. Well, why two frequencies? Well, that's so that they can't be confused with any other frequencies. Noise, interference, all of those things are much harder to, or it's much harder for those things to interfere with a pair of frequencies that uniquely identify what you just did. All right. So, as an example of some of the signals that come to us from the central office, that would be the busy signals or the busy tones that come back. Now, of course, how we do things today is a little bit different than this, but in some cases, when you have a VoIP phone, you push buttons, it's not necessarily frequencies that you're sending, but encoded frequencies that you're sending across. Now, all of that is a little bit much for right now, but that is why we make those funny sounds and things like that, because they're actually sounds that are within the range of human hearing and actually within the range of human speech. Now, pulse dialing, like on a rotary phone, right, you go shh, that's actually interrupting the circuit. The pulses indicate the numbers that you want to dial. Let's talk a little bit more about the geography of the telephone network. Sometimes it's fun to understand a little bit about how these things work, or at least how they work traditionally. So a local access and transport area was one of a collection of hundreds of geographic areas across the United States. And so think of the United States not as a collection of states, but as a collection of these lattices, these little chunks of geographic area. And the idea was that a telecom provider was allowed to offer service inside that lattice. Okay. Now there's two other terms that we're going to introduce here. One is an inter-exchange carrier, an IXC, and a local exchange carrier. And there was a very big deal in 1982 that differentiated very clearly what these folks are, or how these folks are different. A local exchange carrier was supposed to offer just local service. So think POTS, think short-range calling. An inter-exchange carrier, think long distance, was supposed to allow connections between local exchange carriers, and you weren't supposed to do both. Now, there are two flavors of local exchange carrier. One was the ILECs, the incumbents. They were there before this breakup of AT&T, and then there were the CLECs, or the competitive local exchange carriers, that came after. Now, an area code is a prefix that we prepend to a phone number. And an area code is also geographically oriented, but it's much more based on population because there are only so many numbers that can be run from one particular area code. So this is an example. I have no idea how old this is, but this is an example of a couple of lattices that exist in Kansas. And we can see that there's really two and maybe a third one sort of peeking in over here. So these are how the lattices at this time were structured in Kansas. Here are area codes, and you can see that there's more area codes than lattices, and so this makes sense because here in an area where the population is more dense, we need an additional area code. Why? Because we need additional phone numbers. So area codes and lattices, maybe in the beginning they were supposed to overlap, but certainly populations change or increase. In fact, here in New York State, where I am, we had to create a new area code to handle the additional folks. It used to be 315 and 716 here, and then we added 585, or at least reorganized the way that the area codes were because of the population change. Now, as I've said, the telephone network is global. It's an international thing, and everybody's supposed to do it the same way. That's why you can call somebody in a different country. Now, individual countries have their own governing agencies. Here we have the FCC, right? But internationally, everybody's supposed to use a very similar set of rules. So the ITU-T is the one that comes up with all of these rules and the standards that we use internationally. So here are a couple of examples. But if you were going to try to learn more about this, some really good places to start would be the G series, the H series, some of the P series, Q series, and then E.164. Now I just realized that's actually a lot to bite off. So maybe just the G series, the G700 series, and maybe E.164. And we'll talk a little bit more about that here in a second. The lower numbered G series, G701, G702, 703, like that, those are for the structure of our circuits and stuff like that. Some of the codecs that we use all the time, in fact, the PSTN is based on the G.711 codec. And the H series, those are the video codecs. So those are, that's a happy place to go visit if you want to learn more about codecs. But within this collection of standards, we have all of the electrical, the physical, the messaging, and the structure that we need to run the telephone network. And then, of course, legislation, the rules for providing access, things like that, have something to do with the standards development. All right, so maybe we'll get a little better handle on some wiring. Now, I've also said the phrase tip and ring a lot, and we know now where tip and ring comes from, but the wires that we use for a phone really only needs two wires, the red and green pair. So ring is red, and then tip is green. And it's just a positive and negative connection because really what we're doing is we're establishing a circuit between the phone and the central office or the class 5 switch or whatever it is that we're talking about. Now, that's all a phone needs, but of course we've come to know and love, things like this, where we're looking at patch cables or jacks, things like this. And this, of course, has a very particular look and feel to it. 8-pin connector, RJ45 terminated, which is quite a bit different than this guy here, which is a phone cord, which is RJ11 terminated. So RJ45, RJ11, completely different animals. But there's a reason why we have to talk about these, because we eventually integrate the two networks and they have to run, in addition to being side by side, sometimes we try to run one kind of connection over the other, and so we'll see how that works here in a second. Now, when we talk about terminating patch cables like this, we say that we are going to use a particular standard. So the standards that we most often talk about is 568A and 568B. Straight through cables are 568B on both sides. If it was a crossover, it would be 568B on one side and 568A on the other. Now, importantly, we know that Ethernet uses the green and orange pairs. Pins 1, 2, 3, and 6. Well, why did we jump? Why don't we use 4 and 5? That's because 4 and 5, I have no idea if you can see this, but 4 and 5 are the blue pair. The blue pair is for telco. That's tip and ring. So when you're running patch cords like this over a data network infrastructure, you're running pins 4 and 5. Those are actually going to be your tip and ring for your phones. Okay, so that's sort of how they go together. And this is just an image that shows a close-up, right? This is an RJ45 female jack, and this is the RJ45 male, and here is an RJ11. We can see that the RJ11 fits right straight into the middle of the RJ45 port. And this is actually a 4-wire connection, but we're only using 2, and the center 2 pins, well, on that jack it's pins 2 and 3. On the RJ45 is pins 4 and 5, would actually be the telco. And that's where they fit right here, which is why we see a pair, white, orange, and orange, white, green. Wait, where is green? Oh, it's way down here in 6, because we're going to insert the telco pair right here. And then, of course, we have 7 and 8, the brown pair, at the bottom. Okay, so that's kind of how our wiring goes together. So if you're ever in a wiring closet and you see, maybe not only, you won't see this in a wiring closet, right, because the phones are going to be in the offices. But if you ever wonder how the telco is running over the data wiring, now you know, because the pins are reserved. Now, it might also be that the place you're working in has traditional wiring also installed. So you might see in the closet data network wiring and then a completely different set of wiring, very commonly all blue and white for the telephones. Well, let's talk about phone numbers for a sec. Globally, the numbering standard is E.164. That's why I mentioned it earlier. Here in the United States, we use something called the North American Numbering Plan, which specifies how we are going to organize our phone numbers. So there's 3 chunks to a phone number, right? Here is the area code, and we saw that on the maps. They're largely based on population density and our particular, usually smaller geographic area than Alata, which is also kind of funny, which is because it indicates why sometimes very short calls would actually be long distance between a local exchange carrier. So between the area code and the LATA, sometimes you would make a very short distance call and it would actually be long distance just across county lines, or sometimes even across from one side of a city to another, although they try to avoid that. Right? So that's the area code. This second chunk here, this is the prefix, and that's the office code. So this indicates which office is going to be handling this, and we can see we got some rules here. Any X can be a 0 to a 9, but these locations here have to be a range of 2 to 9. So you won't ever see a 1 or a 0 out front here. And then, of course, the last thing here is a station code. Now you could equate that to a circuit, because in the central office, that is punched down, that wire is punched down at a particular location, and it goes all the way out to the end node phone, which is why when you dial 911, they know exactly where you are, and which is also why when you're on a mobile phone or a voice over IP phone, we have to do something about trying to find your physical location. So E911 is the relate there, but also the GPS positioning. When we set up a phone system, we have to set up something called a dial plan, and this is all the numbers that we want to be able to dial internally, but also how we get outside. So 911, and then also just dialing 9 to get out. Then we've got trunk lines, we've got services that we want to offer, you've got maybe modems or fax machine if you still have those around. So these are voicemail. So these are all the things that we need to be included, or need to have included, in something called a dial plan. It's all the numbers that your local phone system has to be able to handle. Now let's talk a little bit about the codec itself. That Another way to think about your local loop, your tip and ring pair coming to your house, is that we're going to encode all of that for transmission over the network. And as I said, it's very common for a local loop to be analog. So your voice data is raw. It's just going right out there just as you speak it. It's just converted to an electrical signal. But we also have all of those DTMF tones plus all of the signaling from the central office. Okay. Now at some point that is converted to a set of digital values. And for a traditional line that happens at the central office on the connection point to the central office, and that's usually handled by something called a subscriber line card. Well, when we're converting from analog to digital, or at the other end you're converting digital back to analog, that's handled with a codec. The codec that we use in the PSTN, or at least the one that was the very traditional one, is G.711. When we do that conversion, that circuit is now converted to something called a DS0, or a digital signal 0. And it is 64 kilobits per second. So that's the data rate. Well, where does that come from? Well, that comes from how G.711 encodes the data. So we actually sample voice. Now the math behind this is by Nyquist and Shannon. So some fabulous reading there for you if you want to learn a little bit more about it. But G.711 says that we're going to sample your voice 8,000 times a second, and then each sample is going to be given an 8-bit value to indicate its amplitude. And so 8,000 samples per second with 8 bits per sample, presto changeo, 64,000. So we call that a DS0. Now just for fun I included this little modem image, and we can see right here that some of the signals that go across there. Why? Because the modem is connecting to a PC's serial port very commonly. So that's what all of these lights are for. The EIA 232 has a bunch of signals that we use. DTR, DSR, carrier detect, transmit data, receive data. So these are all signals that would light up on your modem as your serial port was going through its signals. And then of course you dialed. Now the next step up is a T1. So I call this the base connection because it's really the first maybe digital connection, or the first maybe powered connection. So we've got all these local loop connections going off, right? And eventually they would wind up in a big bundle of wires that were, being sent off to the central office. But at some point we would convert all of those DS0s and local loop connections maybe to a multiplexed connection called the T1. T1 is sort of the base connection that we talk about when we start multiplexing. So this is just showing us that we would multiplex 24 connections together, and that each one of these stations, these local loop connections, these DS0s, would belong to a particular channel in a T1 frame. There's that word. Right, so we build a T1 frame. This little FB out here is called a framing bit, and the T1 uses pins 1, 2, 4, and 5, at least on the 8-pin connectors that we're used to building. Now a lot of times when we're building voice over IP connections, we will wind up using a T1 interface, and a lot of times we'll need a T1 crossover, and so that just is illustrated right down here. Now a T1 is a full duplex connection, so 2 of the connections are going that way and 2 of them are going that way. That's why there's 2 pair. But remember here that we are multiplexing connections, and so in a T1 frame this would be like 8 bits, 1 sample. This would be 8 bits, 1 sample, 8 bits, 1 sample, but all from different DS0 channels. So a little bit more detail about a T1 frame. So it's 24 channels. Now this goes out the window if we start talking about ISDN, but that's not what we're talking about. And then we're still talking about G.711, so each channel is 8 bits. So what we're going to do is we're going to take 24 8-bit samples, right? So we're just going to go through channel 1, channel 2, channel 3 like that. Take 8 bits, and then we're going to add a framing bit. And then we're going to go back and do it again and grab the next set of samples so that we can build another T1 frame. But how do you calculate the T1 data rate? Well, when you're building a T1 frame, right, we're going to take 8 bits from each one of those 24 channels. So 8 times 24, but then we're going to add a framing bit to indicate sort of either the beginning or the end of the frame, depending on how you look at it. Well, that is 193 bits, but we're going to do that 8,000 times a second. So 193 times 8,000 gives us 1.544 megabits per second, which is the T1 data rate. Not the same for E1, different number of channels. Now when you're building T1s, when you're setting them up, there are some additional details, right? There are some different structures, some different signaling that you can use when we are actually going to send the T1 frames across the line. And so a lot of that goes to the number of channels that you're going to use or what your electrical signal is going to look like. So probably the most common T1s that we work with are things that use something called ESF, or Extended Superframe Format, which is these guys here. And then, well, I shouldn't say it that way. That's where we're stealing the least significant bit. When you do bit stealing, what you're doing is you're actually creating a data channel for management traffic. And then for the electrical signal, we do binary 8-0 substitution and alternate mark encoding. And so that's how we do the electrical signal. And here's another look at a crossover cable. So that's how you get the T1 rate, and those are the basics for the T1 characteristics when you're setting up a link. Very, very common set of characteristics. So ESF, AMI, and B8ZS. Now when we're flowing through the entire PSTN, what we have to remember is that we're multiplexing and multiplexing and multiplexing, and so we've got lots and lots of stuff going on. So if we go back to our original 24 channels, right, this channel would appear maybe right here, but then it would go to the next central office or the next switch. And that switch is also collecting all of these T1s from all of its other connections. But then we have to make this routing decision, right? So this phone call right here might be going to Saskatchewan, and this phone call might be going to California, and this phone call might be going to Europe somewhere. So we have no idea where they're going, and so the routing has been set up to forward these particular phone calls to the correct destination. Well, that means that along the way, they're completely reorganized or multiplexed in a different way for transmission to the next step. It's kind of like, I don't know, loading and unloading trucks. Trucks go to the depot, they collect everything from your city, and then they move to the next city. They're unloaded, and the stuff is repackaged into a collection of other different trucks, and then off they go. Well, that's a lot of stuff here. I think we're going to finish up. Well, there we go. That was a little bit on traditional telephony terms and some of the geography and the architecture, and how data and traditional telephony go together. Now, as we move along, I will occasionally refer back to these things, and of course we're just scratching the surface. We're just trying to get enough so that we can understand, you know, how we got to where we are today. And maybe along the way we'll talk a little bit about the internet and how it works. So keep watching to continue your VoIP journey. Hey, like and subscribe if I'm helping or if you're liking the content. And let's make sure those voice packets always reach their destinations, whether they're actually in packets or just analog waveforms.